Let's look at an HSC question on annuities. This is from 2007 and was question 9, so it's considered a more challenging question as it was closer to the end of the paper. Mr. and Mrs. Kane each decide to invest some money each year to help pay for their son's university. The parents choose different investment strategies. Mr. Kane makes 18 yearly contribution of $1,000 into an investment fund. Notice it doesn't tell you this is an annuity. You need to be able to establish that by reading the problem. He makes his first contribution on the day his son is born. This is different to superannuation because your first payment to your super isn't on the day you start working rather than at the end of the first month. While here the first contribution is made on the day the son is born rather than on their first birthday. And his final contribution on his son's 17th birthday, not 18th. His investment earns 6% compound interest per annum. So there is no talk of monthly, we can work yearly. Find the total value of Mr. Kane's investment on his son's 18th birthday. As I said in my previous example, here we have 3 marks. We need to show those 3 steps. Establish a pattern, then state the geometric series, and then give the final value. So let's do this. Let's write a summary. So part 1, the amount that's going in the account is $1,000. The rate is 0.06 per annum, and the number of years is, now that's a bit tricky, is it 18 or 17? Let's write 18 and then we're going to come back and check that. So the first amount is going to be $1,000, and that goes in, actually we might do a timeline, and I highly recommend a timeline for your calculations. That's the 18th. The first amount goes on day 0, $1,000. Year 1, another $1,000. Year 2, another $1,000, and so on. So that first amount accumulates interest for 1 year, 2 years, 3 years, all the way to the 18th year. So that would be 1.06 to the power of 18. The second amount is again another $1,000, but that's in the bank account for 1 less year. So 1.06 to the power of 17. Amount 3, $1,000, 1.06 to the 16, and so on. So again, I demonstrate for 3 and then jump to my last. So the last one is $1,000, and that was on the 17th birthday. So that sits in the bank account for 1 year. Now, is that A17 or A18? Since this first 1,000 we labeled A1, the second one we labeled A2, even though that's the second 1,000, so the 17th one will be A18. The 0th one was A1, the first birthday was A2, 17th will be A18. Total amount is going to be all of those added. All of them have $1,000. Can take that out as a factor, and I'm actually going to now write my series from smallest index to the largest. 1.06 to the power of 18. So hopefully you can see there are 18 terms. We're starting with 1, 2, and so on all the way to 18. We need to write this is a geometric series. My first term is 1.06. My ratio is 1.06. And the number of terms is 18. So, total is 1000 times the equation again is A 1.06 R 1.06 to the power of n minus 1 all over 1.06 minus 1, which is 0.06. We can calculate that, giving me $32,760 to the nearest cent. Word question, we need to give word answer, find the total value of Mr. Kane's investment. So okay, let's go to part 2. Now Mrs. Kane makes her contribution in a different fund. She contributes $1,000 on the day of her son's birth and increases the contribution by 6% each year. Her investment also earns 6% compounded per annum. Find the total value of her investment. On her son's 3rd birthday, just before she makes her 4th contribution. So a little bit more challenging, but this is only worth 2 marks. So let's write a summary of the information. The first contribution is going to be $1,000. Part 2. But I'm going to make a note, increases by 6% every year, just so I don't forget. So let's establish a timeline. At the birth, Mrs. Keynes makes an investment of $1,000. At first birthday, she increases that investment by 6%. So it's now $1,000 times 1.06. So it's the original plus another 6% on top. At the second birthday, it's $1,000, 1.06, now increased again, so that would be 1.06 squared. And then at the third birthday, that's when we want to know the amount before the next payment is made in the bank account. So let's make a list. Don't forget our rate of return is 0.06 per annum. So amount 1 was $1,000 that was invested at 6%, and it sits in the bank account for 1, 2, 3 years. Amount 2 is $1,000 times 1.06, and that sits in the bank account for 2 years. That simplifies to 1,000, 1.06 to the power of 3. And amount 3 is 1,000. What did we have on our timeline? Here it is, 1.06 squared, and that sits in the account for 1 year, 1.06. So that's 1,000, 1.06 cubed. So the total by the third birthday is 1 plus 2 plus 3. Now they're all the same, so essentially we have 3 lots of 1,000, 1.06 to the power of 3. You can work that out, and that's $3,573.05 to the nearest cent. Now go back to the question. The total value of Mrs. Kane's investment on her son's 3rd birthday is, therefore, so now we need to go to the last part, which is Mrs. Kane also makes her final contribution on her son's 17th. Find the total value of Mrs. Kane's investment on her son's 18th birthday. So no investment being made on the 18th birthday. Just like before, now that considering this is only worth 1 mark, all we need to make sure we do is we get the number of terms right. So on the son's 3rd birthday, we had 3 terms. So on the son's 18th birthday, we are going to have 18 terms. And since we've established the pattern, it's just 18 times 1,000 times 1.06 to the power of 18. So we establish that pattern here, A3, 3, 3. So A18, 18, 18. And that gives me $51,378.10 to the nearest cent. And as always, we need to finish with the sentence. Now we can see the significant difference between the two amounts, 51,378 as opposed to 32,760. But the question didn't require that comparison.